Good morning, all of you. Welcome to Sri Jayendra Rank Zone. We are discussing Electrochemistry, Lecture 3. So, in the previous lecture, we have already discussed about Faraday's laws and Colas law. Now, we are going to discuss the next topic in this chapter. So, what is electrode potential? So far we have completed Faraday's laws, and in the first lecture we have completed electrolysis and Faraday's laws. Second lecture we have completed conductivity, conductance, Colas law, etc. And in third lecture now we are doing electrode potential. This is very important topic. So what is electrode potential? So electrode is an arrangement where metal is dipped in a solution containing its own ions. So metal dipped in metal. For example, copper or dipped in copper metal. So copper or dipped in copper sulfate solution, like that. So electrode is an arrangement where metal is dipped in a solution containing its own ions. So example, when a copper rod is dipped in copper sulfate solution, so it gives out copper ions. So electrode potential is a potential developed at equilibrium. So it is a potential developed at equilibrium between metal and metal ions when a metal is dipped in a solution having its own ions. Point. Electrode potential is a potential developed at equilibrium between metal and metal ions when a metal is dipped in a solution having its own ions. So due to the ions, when you dip a metal, suppose for example, as I told you, when copper rod is dipped in copper metal, so that is copper sulfate solution, what happens? Copper ions will start migrating. So it ionizes and forms copper ions. And this copper ion, due to the movement of these copper ions, current is developed. And as the current is produced, electrode potential, that is even there maintains a potential. A potential difference is developed across the end. So this is called electrode potential. It is the potential developed at equilibrium when between metal and metal ions when a metal is dipped in a solution having its own ions. So this is called electrode potential. When the concentration is 1 molarity, the electrode is standard electrode potential and the potential is called standard electrode potential. I hope it is clear. So when the concentration of the solution is 1 molarity, then whatever the potential difference developed is called electrode potential and it is also called as standard electrode potential. So standard electrode potential will maintain standard electrode potential. Next. According to IUPAC convention, only standard reduction potentials are used for calculations. According to IUPAC convention, only standard electrode potential, standard reduction potential are used for calculations. So standard reduction potential is important. According to IUPAC convention, only standard reduction potentials are used for calculations. So we'll use reduction potential. What is reduction potential? Losing of electrons. The electrode where oxidation takes place is known as anode. Very important. The electrode where oxidation takes place is known as anode, and the electrode where reduction takes place is known as cathode. So, anode and cathode. Next, we have a device used to convert the chemical energy produced in the redox reaction into electric energy is called as an electrochemical cell. So, very important. So, a device used to convert the chemical energy produced in a redox reaction into electric energy is called as an electrochemical cell. So normally electrolysis is different, electrochemical cell is different. Because in electrochemical cell, chemical energy is used to convert electric energy. So for example, you can see the remote batteries, pencil cells, okay, all these galvanic cells, voltaic cell, all these are coming under electrochemical cells. So these are also called as galvanic cells or voltaic cell, Daniel cell, Leclan cell, etc. Next we have very important in this. A device used to convert chemical energy produced in a redox reaction into electric energy is called as galvanic cell. Now we have what is a galvanic cell. Very important. This is all of you listen carefully. This experiment I will be explaining here. Easy it is. So a galvanic cell consisting of zinc or dipped in zinc sulfate solution. Here this is called zinc or dipped in zinc sulfate solution, and this is called copper or dipped in copper sulfate solution. And both the molarities, 1 molarity zinc sulfate, 1 molarity copper sulfate. And this zinc rod is connected to the battery, and is connected to the positive terminal of a battery, and copper rod is connected to the another battery. And these two are connected by means of salt pitch. This is called salt pitch. I hope it is clear. So this is called salt pitch. So zinc rod dipped in zinc sulfate solution and copper rod dipped in copper sulfate solution, and these two are connected by the means of salt pitch. And a voltmeter is kept here. It is no battery, just they will be connected to a key. So here battery is not being introduced. Just copper rod dipped in copper sulfate solution, zinc rod dipped in zinc sulfate solution. So what happens first? What happens? Zinc ions. Zinc changes to zinc ions. Zinc changes to zinc ions. And what is the use of this salt pitch? Salt pitch is a device which is nothing but charge carriers. Means, for example, here copper ions have been carried out into zinc rod by means of salt pitch. So initially, what happens? And salt pitch is a device, is a U-shaped tube which is made up of jelly-like substance called agar-agar mixed with potassium nitrate and or silver nitrate. So agar-agar jelly-like substance mixed with potassium nitrate. This is nothing but salt pitch. And salt pitch is nothing but here to maintain electrical conductivity. To maintain electrical conductivity, we have to use salt pitch to maintain conductivity or to migrate the ions from one place to another place. So that is called salt pitch. So first, what is the assumption? Zinc or dipped in zinc sulfur solution, copper dipped in copper sulfur solution. So what happens? Initially, copper ionizes to form copper ions. These copper ions will go by the means of salt pitch goes to zinc rod, and there zinc will get ionized by the means of copper, and copper ions gains two electrons here and forms copper here. Copper ion changes to copper, which is undergoing reduction because gaining of electrons is called reduction and losing of electrons is called oxidation. On the whole, it is a redox reaction. And due to the migration of ions, that is copper ions, a voltmeter, you will notice a deflection in the voltmeter, which nothing but potential difference is developed and the current is produced. Potential difference is developed and the current is produced. So this is nothing but a device which converts chemical energy, that is zinc sulfate and copper sulfate is giving ions. So chemical energy is converted to electric energy. How we can identify electric energy? By the deflection voltmeter, or even if you keep here ammeter also, you can notice the deflection. So it is clear now. So what is the function of salt pitch? We'll discuss later. So salt pitch is a U-shaped tube which is made up of jelly-like substance called agar-agar mixed with potassium nitrate. Potassium nitrate, and here potassium chloride also they have taken. So Cl minus and K plus because they also get ionized in the solution. Zinc taken zinc sulfur solution and copper dipped in copper sulfur solution. Initially, first what happens? The copper ions will be formed because of its high conductivity. Copper sulfur dissociates to form copper ions, and these copper ions, by the means of salvage, goes to anode, that is zinc rod, and copper ions because of cathode. So the copper cathode and anode zinc. And these copper ions will go to zinc rod. There it ionizes zinc to zinc ions and itself getting undergoing reduction and forms copper. So due to the migration of ions, current is produced in the galvanic cell. And this current is produced due to the chemical energy only. So on the whole, we can say it is nothing but a galvanic cell or a Daniel cell is our electrochemical cell is nothing but it is a device which is used to convert chemical energy into electric energy. And how can I identify electric energy? By the deflection voltmeter, because current is there, then only voltmeter gets deflected. And a voltmeter is a device which is used to measure potential difference between the electrodes. And whatever the electrode potential developed is called as standard electrode potential and our electrode potential. Simply electrode potential will say. I hope this is clear. This is called galvanic cell or Daniel cell or electrochemical cell. So an electrochemical cell is a device which is used to convert chemical energy into electric energy. How we got chemical energy? Because zinc sulfate and copper sulfate is solutions of 1 molarity has been taken, and due to this zinc rod and copper rod is kept in their respective solutions, and due to this what happens? These ions will be formed. The movement of ions is nothing but generating producing current, and the current will be in the opposite direction because of movement of ions, positive ions to negative ions, and current will flow from negative to positive. So this is clear. So this is called galvanic cell or Daniel cell or electrochemical cell. Next. A standard NNCl is made up of standard zinc electrode and a standard copper electrode. These two electrodes are connected by using a salt pitch. Zinc electrode is anode and oxidation takes place. Copper electrode is cathode and reduction takes place. As I already told you, zinc electrode is anode where oxidation takes place. Always at anode, oxidation takes place, and at cathode, reduction takes place. And what is oxidation? Losing of electrons. Or you can see the oxidation state. Increase in oxidation number, or losing of electrons. Both are nothing but so increasing oxidation number and reduction. Oxidation and reduction both are very important. So increase in oxidation number, I'm writing here, increase in oxidation number is called oxidation, and decrease in oxidation number, decrease in oxidation number is called oxidation. So reduction. I hope it is clear now. So what happens in Daniel cell or electrochemical cell? The two electrodes are connected by using a salt bridge, and at zinc electrode, oxidation takes place, and copper electrode, reduction takes place. Next. Yes. So what is anode reaction? Zinc loses two electrons and forms zinc ions. And cathode reaction, copper gains two electrons and form copper ions. The net cell reaction is zinc plus Cu plus 2. This is very, very important. Zinc on reaction copper ions forms copper metal and zinc ions. By this, what you can understand, zinc is giving reduction to copper ions. Zinc is reducing copper ions to copper and itself undergoing oxidation because zinc is changing to zinc ions. So if you see the oxidation state of zinc 0 to here it is 0 and here it is plus 2. It is already given. And here it is plus 2. So here it is 0. So zinc is undergoing increase in oxidation number and copper is undergoing decrease in oxidation number. So decrease in oxidation number is called increase in oxidation number is called oxidation and decrease in oxidation number is called reduction. I hope it is clear. So this is called the net reaction taking place in the electrochemical cell or Daniel cell. And due to the movement of these ions only, it produces current, and as the current is produced, definitely it develops a potential difference, and you can see the deflection in the voltmeter. And the whatever the voltage developed by the cell is almost equal to 0.05, 0.5 volts. Next. So how the galvanic cell is represented, very, very important this also, because if you don't know representation, you cannot substitute the numericals. A galvanic cell is represented as metal to metal ion with concentration, you have to write it in brackets. Salt pitch is indicated by double line. Double vertical lines is nothing but salt pitch. It indicates nothing but salt pitch is present. And metal ion, that is the reduction, and concentration, that is concentration means here the concentration will be kept in, that is molarity is kept in brackets, and metal. So right hand side we have to write, right hand side this is called reduction. Always right hand side cathode, left hand side anode. Right hand side cathode where reduction takes place, and left hand side anode where oxidation takes place. So always first metal, vertical line, metal ion. Double vertical line, nothing but salt pitch, metal ion, concentration, vertical line, then metal. So this is the representation. For example, in the previous reaction, you can see zinc is undergoing oxidation and copper ions is undergoing reduction. So automatically we can write zinc changes to zinc ions, 1 molar to solution, salt pitch, copper ions, 1 molar to solution changes to copper. So that vertical line represents changes to vertical line, single vertical line represents changes to. So in this you can say zinc changing to zinc ions, 1 molarity concentration, salt pitch, copper ions changes to copper metal, 1 molarity solution. So the EMF of the cell is given by EDQ of cell is equal to EDQ of right minus left, that is cathode minus anode. EDQ of right minus left. Right means what? We have cathode, and left means what? We have anode. So EDQ of cathode minus EDQ of anode for all reduction potentials when the reduction potentials are given. So what is reduction potential? The potential difference developed in reduction The potential difference developed in reduction process is called as reduction potential. How can I say reduction potential? Because here plus 2 changes to 0. Here as it is plus 2 changing to 0, copper metal. Definitely we can say it is undergoing reduction. And what are the potential difference developed at this process? It is called as reduction potential. Reduction potential, I'm writing here RP. RP, reduction potential, and here it is OP, oxidation potential. So reduction potential of cathode minus reduction potential of anode. Here also this is also reduction because zinc changes to zinc ion. If you don't know how to identify what is given reduction potential and oxidation potential, you'll get wrong answers in this type of numericals. So here both they have given reduction potential, but this is reduction potential of cathode and this is reduction potential of anode. So in this way, we will represent a cell. So how a galvanic cell is represented? Left hand side we have to write oxidation process. Right hand side we have to write reduction process. So that vertical and single vertical line represents changes to double vertical line represents salt pitch. So I hope it is clear. Next, what is salt pitch? As I told you, salt pitch is made up of potassium chloride or potassium nitrate with agar-agar jelly-like substance. Agar-agar is a jelly-like soft substance. It is jelly-like substance. Agar-agar means jelly-like substance. They'll ask the function of salt pitch, jelly-like substance. So JELLY, jelly-like substance. It is called agar-agar. So they'll ask the function of salt pitch in the galvanic cell as an objective question. So these all the points are important. So what is the importance of salt pitch is? It is used to establish the electrical contact between two half cells because of the migration of ions by the means of salt pitch. We can say it is used to establish the electrical contact between two half cells and maintains the electrical neutrality of the solution in two half cells, and it is used to eliminate liquid junction potential. It is used to eliminate liquid junction potential, and these are the 3 points. Apart from this, so maintain electrical neutrality and establish current between them. So these are functions of salt pitch. Now we'll see the questions. In the voltage, the cell reaction is given like this: Mg plus 2Ag plus gives rise to Mg2 plus 2Ag. Represent the cell using symbols and write the electrode reaction. Simple it is. Just we have to write the in galvanic cell representation. Here by from the diagram, from the equation, we can say magnesium oxygen state is 0 because the oxygen state of single element is always 0 and it is changing to plus 2. So it is already given. And silver plus 1, it is changing to 0. So this is called voltaic cell reaction. So we can write here magnesium is undergoing oxidation and silver is undergoing reduction. Silver is undergoing reduction. So oxidation should be written on the left hand side and reduction should be written on the right hand side with concentrations. So we can write the cell reaction Mg vertical line Mg plus 2 because they are not mentioned concentration. So directly we can write Mg plus 2 salt pitch double vertical line 2Ag plus Ag plus. No need to add 2 because here stoichiometric coefficient only in the substitution part we will use. So Ag plus changes to Ag. Salt pitch. The salt pitch is already given. So Ag plus vertical and single vertical and Ag. This is the cell representation using symbols and write the electrode reactions. So electrode reactions you can write here at anode. At anode, magnesium gains 2 electrons. Mg plus 2 electrons. Sorry, Mg gives rise to Mg plus 2 because it loses 2 electrons. So this is nothing but Mg2 plus oxidation takes place. Mg plus 2. Similarly, plus 2 electrons. Next at cathode, how to write cell representation. At cathode already we know silver changes. So 2Ag plus, here we have to use 2Ag plus 2Ag plus gains 2 electrons and forms 2Ag neutral 2Ag because 1 Ag is gaining 1 electron, 2 Ag means gaining 2 electrons. The 2 electrons is coming from magnesium. So this is clear. So in this way you have to write cell representation as well as reactions at cathode and anode. So this is the voltaic cell reaction is given and they are asking us to find represent the cell using symbols and write the electrode reactions. So the electrode reaction means at anode and at cathode. And cell representation, always left hand side oxidation, right hand side reduction. Oxidation means Mg changes to Mg plus 2, and reduction Ag plus changes to Ag. I hope it is clear. Next. So answer you can see, as I told you. So oxidation reaction and reduction reaction. And very important, we will not write the stoichiometric coefficient in the cell representation. That is Ag plus means we have to write only 2 Ag plus, we cannot write. Cell reaction we can represent, but at the salt, this galvanic cell representation, we don't want to, means we should not use the coefficients. That is Ag plus change to Ag only, simply have to write. Should not write 2 Ag plus gives rise to 2 Ag. Only for reduction reaction, we can write 2 Ag plus gains 2 electrons and forms 2 Ag. And oxidation reaction, this is at anode, Mg changes to Mg plus 2 electrons. So always losing of electrons is called oxidation, and gaining of electrons is called reduction. Losing means left hand side we have to write minus. So that minus, if you bring right hand side, we'll write plus 2 electrons, because we cannot write minus in a equation. So I hope it is clear. Next. Write the cell reaction and the electrode reactions for the following cell. They have given cell representation and they are asking us to write cell reaction. First, we'll concentrate on cell reaction. From this, we can easily understand. Aluminum changes to aluminum plus 3 and Ag plus changes to Ag. Means here aluminum is reducing silver ions to silver and itself getting oxidizing. So simply you write Al plus 3 Ag, because it is donating 3 electrons, gives rise to 3 Ag plus Al plus 3 plus 3 Ag. So this is the actual cell representation, because aluminum is changed from 0 to plus 3. You can see here it is 0 to plus 3, and Ag plus changes to Ag. So it is changing from plus 1 to 0. So for silver it is undergoing reduction, for aluminum it is undergoing oxidation. So aluminum changes to Al plus 3. So Al plus 3 means it should lose 3 electrons, and those 3 electrons will be gained by silver ions. So 3 Ag plus it becomes 3 Ag plus gains the 3 electrons and forms. So at anode, at cathode, what happens? 3 Ag plus gains 3 electrons. 3 Ag plus gains 3 electrons and forms 3 Ag, 3 Ag. And Al at anode, aluminum loses 3 electrons and forms Al plus 3 electrons, because losing means you have to write on the other hand side, on the right hand side, plus 3. So this is the cell representation, cell reaction, as well as electrode reactions. I hope it is clear. So from seeing the cell representation, we can write cell reactions, and finally we can write the equation also. And also by giving the equation, this is the equation. In the previous question they have given the equation, they are asking us to write cell representation as well as reactions at cathode and anode. So always at cathode, gaining of electrons takes place, and how many electrons, that we can see by the using the charge. And at anode, losing of electrons, and how many electrons also we can see the charge. Simply if you write for all the things, simply if you write the oxidation number, here aluminum is 0, it is plus 3, and here it is plus 1 and it is 0, because the oxidation number of a single element is always 0. So in this way you can write. If you know this, easily you can understand which is cathode, which is anode. And if you don't know which is cathode, which is anode, it's very difficult to apply the formula for finding electrode potential of the cell, that is E degree of cell, which is equal to E degree of right minus E degree of left. So to know that, at least compulsory to substitute the values clearly, you should know cell representation, cell reaction, reactions at cathode, reactions at anode. So this is the cell reaction, Al plus 3Ag plus gives us to Al plus 3 plus 3Ag. And next, calculate the cell potential. Here it is very interesting question. Calculate the cell potential of a cell obtained by the combination of standard silver electrode and standard copper electrode. Very important question. Here they have given reduction potential of silver, that is Ag plus changes to Ag gives us plus 0.8 volts, and reduction potential of copper is also given, Cu plus 2 Cu gives us plus 0.34 volts. And they have both, they have given reduction potential, but we have to decide which is cathode, which is anode. So for this, we have to remember electrochemical series, or simply if we don't remember electrochemical series also, we can decide which is cathode, which is anode. Suppose when two positive values are given, when the reduction potentials are two positive, the reduction potential with less positive is taken as anode, and the reduction potential with more positive value should be taken as cathode. Very important. I'm writing the statement. When, just to note down this statement in your classwork, I'm writing here clearly. When reduction potential of two reduction potentials of two electrodes are given positive values, positive values, comma, the electrode potential with more positive value should be taken as cathode. The electrode potential with more positive value, very important this one. If you don't remember the electrochemical series also, we can use this. The electrode potential with more positive value is taken as cathode, and the electrode potential, that is reduction potential with less positive value, electrode potential, that is reduction potential with less positive value, should be taken as anode. So you know right and you know left. So anode becomes right and cathode becomes left. So for this question, EDQ is equal to EDQ of cell is equal to, that is standard cell potential is equal to C, EDQ of cell is equal to copper first. So first is silver, because right minus left, right is becomes silver and left is copper. So simply connect 0.8 minus 0.34, which is equal to, so here 6 40, so 0.46 volts. 0.46 volts is equal to. So I hope it is clear. Just note it down. This statement is very important. When reduction potentials of two electrodes are given positive values, the reduction potential with more positive value is taken as cathode, and the reduction EP or electrode potential or reduction potential, here I'm discussing both are same here, and the reduction potential with less positive value is taken as anode, because they are not given the cell reaction and they didn't mention which is cathode, which is anode. We have to remember either electrochemicals is stable, or if you don't remember that electrochemicals is stable also, by using the values you can say which is cathode, which is anode. Here by this we can say copper is displacing silver, so copper is bringing reduction to silver ions and changes to silver metal, whereas copper itself are getting oxidation and forms copper ions. So on the whole, the reaction is, here I'm writing the reaction, Cu plus Cu, Cu only, copper plus 2Ag plus, because it is gaining 2 electrons, gives rise to Cu plus 2, because it is losing 2 electrons, plus 2Ag. So this is a cell reaction. So if they are given cell reaction, easy, we can understand. We can write that in galvanic cell representation, we can find. But here they have not given any cell reaction. Simply they have given reduction potential of silver and reduction potential of copper. And by joining these two cells, obtained, they are asking us to find cell potential obtained by the combination of these two cells. So that's why we have to do like this. So when they are not given reaction, we have to write, when reduction potential of two electrodes are given positive values, the reduction potential with more positive value is taken as cathode, and the reduction potential with less positive value is taken as anode. This point is very, very important. Mark a note in your classwork. I hope it is clear. Next. So answer is 0.46 volts. Next question. So here the question is not there. So what are the difference between electrochemical cells and electrolytic cells? So electrochemical cell and electrolytic cell. Electrolytic cell already we discussed in the first session. That is nothing but electrolysis takes place. Means there what happens here, current is produced. Means here they convert electric energy into chemical energy, because to produce metals we will use that electrolysis process to produce metals. So that's what basic idea is, nothing but here current is produced, means current is given to produce metal. So nothing but what here, that is nothing but electric energy is converted into chemical energy. And in electrochemical cell, as we see, chemical energy is converted into electric energy. That is the main difference. So here electric energy is released, electric energy is released in the cell as a result of redox reaction which takes place. And electric energy is taken up. Here it is released and here it is taken up in order to bring about the redox reaction. So in both the cases, redox reaction is common, but In both the cases, redox reaction is common, but here, first case, that is electrochemical cell, chemical energy is converted into electric energy. Means electric energy is released, it is produced. Whereas here, electric energy is used up, taken up in order to bring about the redox reaction. Next, second point, the redox reaction is spontaneous in nature, and the redox reaction is also here non-spontaneous in nature because current should come, then one should deposit at cathode, one should deposit at anode, then finally they will combine. Next, third difference, the two electrodes are generally suspended in separate beakers or half cells by using salt bridge. Whereas here the two electrodes are kept in only same beaker, that is electrolytic cell, which is either molten or in aqueous solution. This is the important point here. So here electrolyte is been dissolved in a solution and in the same beaker only we'll take cathode as well as anode. But here we are suspending it in two different beakers. Anode is negative pole while cathode is positive pole because anode is negative pole because here, very important point. In electrochemical cell, anode is negative pole, while cathode is positive pole. Whereas in electrolysis, anode is positive electrode because it is connected to the positive terminal of the battery, while cathode is negative electrode because it is connected to negative terminal of the battery. So this fourth point is very important. You can concentrate. In electrochemical cell, anode is negative pole, while cathode is positive pole. Whereas in electrolytic cell, anode is positive electrode, while cathode is negative electrode. Very, very important point. Next difference, the electrons move from anode towards the cathode. This is also very important here because in galvanic cell, what happens? Copper first changes to copper ions. That copper ions will go to from cathode to anode. So when the ions are going from cathode to anode, electrons will move from anode to cathode. So opposite direction, that is convection current. So the electrons move from anode towards cathode in the external circuit, and the electrons are separated by the external source, that is battery, enter through the cathode and are released at the anode. This fifth point is most important. Just to make a note. This point you will not find in textbooks or any other materials. So that's why this is made specially for you. The electrons move from anode towards the cathode in the external circuit in electrochemical cells, whereas the electrons are supplied by external source, enter through the cathode and are released at the anode. Very, very important point. Next, a salt bridge or a porous pot is used to separate the two half cells, and no salt bridge or porous pot is needed in this case, as you already know. So these are the main differences between electrochemical cell and electrolytic cell. Next. So how to measurement of electrode potential? The absolute value of electrode potential cannot be determined. Only the difference in the electrode potentials when two electrodes are connected can be determined. A reference electrode should be used to determine relative reduction potential. So how we are measuring the reduction potentials? We have like how we are measuring atomic weights by using carbon 12 atom. The same way here also we require a reference electrode should be used to determine relative reduction potential of electrodes, and that reference electrode is nothing but C, that is standard hydrogen electrode. Standard hydrogen electrode is also called as SHE. So standard hydrogen electrode is used as reference electrode for which the reduction potential is zero. So whatever the standard means, how it is taken as reference electrode and its value is taken as 0 volts. Very, very important. So always hydrogen potential means if you take hydrogen gas and H plus ions by keeping 1 atmosphere and 1 molarity. The electrode reaction is like this. This is single electrode reaction, that is H plus gains electron and forms half of H, that is hydrogen atom. And this, whatever the potential difference developed in this reaction is nothing but it is taken as zero. So that's why the standard reduction potential C is represented as like this. So H2 and H plus, only single electrode potential. Salt bridge will be kept, but we should not write this because it is not a complete reaction. So this is nothing but here, this is the experiment here. Hydrogen gas is taken. So this is the platinum rod and hydrogen gas is taken in a solution which contains HCl. So what happens here? After some time, you notice that at 1 atmosphere or 101325 pascals, using platinum rod, what happens? You'll see the bubbles here. And the bubbles is nothing but the formation of bubbles means hydrogen gas is introduced. And this, when hydrogen gas is introduced into the container, this hydrogen gas changes to H plus ions, H plus ions. And this H plus ions is nothing but 0 to 1. So increasing oxidation number. So oxidation takes place on the whole reduction takes place. And here, and this H plus ion changes to hydrogen atom by use of platinum. And whatever the potential difference developed in these whatever the potential difference developed in this experiment is taken as zero. Is taken as zero. So always for hydrogen electrode, if you take hydrogen as electrode, either cathode or anode, if you take in the reaction, its potential difference should be taken as 0 volts only. That is what it is called, reference electrode, and also called as standard hydrogen electrode. I hope it is clear. So in this, hydrogen electrode is important. Next. So continuation to the topic, that is electrode potential. So what is electrode potential? Basically, the potential difference developed by an electrode in the electrochemical cell is called electrode potential. In other words, I'll tell you simply, what is electrode potential? The potential difference developed by an electrode in a electrochemical cell is called as electrode potential. So it can be oxidation or it can be reduction. So by saying the question, we can say whether they are given oxidation potential or reduction potential. Usually they will give reduction potentials. Even if they are given oxidation potentials also, we can change them into reduction potentials. Now next we have the She is coupled. She is nothing but what? Standard hydrogen electrode is coupled with electrode for which the potential is to be determined. The EMF of the cell is determined experimentally depending upon whether she is anode or cathode in the combination. Here I told you whether they are given anode reaction or cathode reaction. The electrode potential of the other electrode can also be determined. So how to determine the electrode potential? Determination of electrode potential of copper. A standard copper electrode is coupled with She. So to determine only copper electrode potential, how to do it? So it is coupled with standard hydrogen electrode and the EMF is determined. So here what happens here, hydrogen is reducing copper because the reaction you can see H2 changes to H plus ion and Cu plus to change to Cu. It means hydrogen is giving reduction to copper ions to form copper and itself getting oxidation because H2 changes from 0 to plus 1 whereas Cu plus 2 changes to plus 2 to 0. So this is called reduction, this is called oxidation, and this is cell representation. So simply you can take EDK of cell is equal to EDK of copper because cathode minus anode. And already we know EDK of H2 cell. Always electrode potential of hydrogen is equal to 0 because it is taken as 0 volts. And EDK of cell, total cell is equal to, so EDK of Cu plus 2 to Cu is equal to EDK of cell, that is equal to 0.34 volts. So in this way, we'll measure the electrode potential of copper, zinc, aluminum, any other metals. So all the metals electrode potential, how to measure? By coupling it with standard hydrogen electrode. Simply we can do it. So I hope it is clear. So that's why for zinc, because zinc is more electropositive than hydrogen, what happens? Hydrogen changes to H plus will go to cathode and zinc changes to zinc ion will go to anode. So due to this, you will get negative value for zinc. So high reactive metals will have negative electrode potential values, negative reduction potentials, and low reactive metals, that is low display metals, will have positive electrode potentials, that is reduction value. So this will discuss next. So zinc, I told you, as I told you, zinc. So zinc is more electropositive than H plus. So what happens here? Zinc is undergoing. So zinc, to determine the electrode potential of zinc, a standard zinc electrode is coupled with She, and EMF is determined. So coupled with She means standard hydrogen electrode. Already we know standard hydrogen electrode is 0. So 0 minus E degree of zinc plus 2 zinc ion. So zinc plus 2 zinc ion is equal to minus E degree of cell, which is nothing but that cell after experimentation we got, after experiment we got it is equal to minus 0.76 volts. So this is nothing but standard zinc electrode with She and EMF is determined. And by coupling these two reactions, we can find out electrochemical series. So as I told you, if you don't remember electrochemical series also, I have given the suggestion how to identify which is cathode, which is anode. And this electrochemical series is nothing but the arrangement of different electrodes in the order of increasing reduction potential. You can see here, this is increasing reduction potentials. Very, very important. Now we are going to see the electrochemical series. So the features of electrochemical series. The series is the decreasing order of chemical reactivity. The series is the decreasing order of reducing power of a metal. And a metal having negative reduction potential, as I told you, this point is important. A metal having negative reduction potential, like in the case of zinc, zinc changes to zinc ions. So zinc ions changes to zinc, it is minus 0.76 volts. So a metal having negative reduction potential like zinc ions can liberate hydrogen from dilute acids, and a metal with positive reduction potential value cannot liberate hydrogen from acids. Hydrogen can liberate those metals, but hydrogen cannot be liberated from those metals. So I hope it is clear. So that's why for copper, it is copper is giving hydrogen. No, hydrogen is liberating copper ions, copper metal from copper ions. Whereas in the case of zinc, zinc is liberating hydrogen gas. So can liberate a metal having negative reduction potential can liberate hydrogen from dilute acids, and a metal with positive reduction potential cannot liberate hydrogen from dilute acids. So I hope it is clear. This point is very, very important. You make a note, and this point I'm writing here. So this point is very, very important. A metal having negative reduction potential is most important. A metal having negative reduction potential can liberate hydrogen from dilute acids, and a metal having positive reduction potential cannot liberate hydrogen gas from acids. So I hope it is clear. Next, a metal can displace another metal having higher reduction potential from the salt solution of the later metal. So here a metal can displace another metal having higher reduction potential from the salt solution of the later metal. This is called as selective discharge theory. Here I'm writing here selective discharge theory. Selective discharge theory. Selective discharge. So what is selective discharge theory? A metal can displace another metal having higher reduction potential from the salt solution of the latter metal. For example, zinc can displace copper from its salt solution. Example, zinc being higher reduction potential, having higher reduction potential, it can displace copper from its salt solution. But copper cannot displace zinc from its salt solution. So for example, zinc can displace copper from zinc sulfate as copper sulfate solution. The reaction can be Zn plus CuSO4. Here I'm writing on the top. You can just see two reactions I'll show. Zn plus CuSO4 gives rise to ZnSO4 plus Cu. Why are you keeping bracket? I'm going to keep bracket. So ZnSO4 plus Cu. And here I'm writing one more equation. CuSO4 plus Zn gives rise to ZnSO4 plus Cu. So carefully observe these two reactions. This is equation 1 on the top, equation 2 at the bottom. So first reaction is possible because zinc is having higher reduction potential, so more negative value. So zinc can displace copper from its salt solution, but copper cannot displace zinc from its salt solution. So copper sulfate cannot displace zinc here. So in the second reaction, sorry, this reaction I have to write like this. I'm rubbing it. Second reaction, I'm changing it. You see here, second reaction, because here also and top is same. Just a little bit confusion is there. So I'm writing again. ZnSO4 plus Cu. ZnSO4 plus Cu gives rise to CuSO4 plus Zn. So this reaction is not possible. It is not feasible because from this reaction we can understand zinc sulfate is a salt solution of zinc and copper is a metal. And here by seeing this reaction, copper is changed to copper sulfate and zinc sulfate changed to zinc. Means by this what we can understand, zinc sulfate is reducing to zinc by using copper, which is not at all possible because copper is below in the electrochemical series and zinc is above in the electrochemical series. And zinc, a metal can displace another metal having higher reduction potential from the salt solution of the latter metal. So this point is clear. So based on this point only, they ask in the examination objective questions, which are the following reactions are feasible, which are the following reactions are not feasible. They'll give 2-3 equations. For this type of questions, definitely you have to remember electrochemical series. So what is electrochemical series table also I have given at the last. I'll show you that table. Easily can understand. And in this reaction, I told this point, zinc plus copper sulfate gives us zinc sulfate plus copper. This reaction is possible. Whereas zinc sulfate plus copper gives us to copper sulfate plus zinc. It is not possible, not feasible. So I hope this is clear. And this is called as selective discharge theory. According to selective discharge theory, the metal which is high in the electrochemical series can displace the metal which is low in the electrochemical series from its salt solution. I am writing here the statement. A metal, selective discharge theory statement, a metal which is placed high in the electrochemical series, which is placed high in the electrochemical series, in the electrochemical series, can displace a metal, can displace a metal. This statement all of you write down in your classwork. Can displace a metal which is low in the electrochemical series, which is low in the electrochemical series, ES, that is electrochemical series, from its salt solution. From its salt solution. Its is important. That is a latter metal. So zinc can displace copper from copper sulfate solution, but copper cannot displace zinc from zinc sulfate solution. This is very, very important. So a metal can displace another metal having higher reduction potential from the salt solution of the latter metal. And we can predict the spontaneity of a redox reaction by using electrochemical series, because spontaneity means which is spontaneous. If the reaction is taking place, then only we can see it is spontaneous. Like in the case, in the previous example I told, ZnSO4 plus Cu gives us CuSO4 plus Zn. ZnSO4 plus Cu gives us to CuSO4 plus Zn. That is the one which is not feasible, I said, that is non-spontaneous. So we can predict the spontaneity of a redox reaction by using electrochemical series. If the half cell potential is positive, then it is a stronger reducing agent than H plus and H2 couple. If the half cell potential is negative, then it's a weaker reducing agent than H plus and H2 plus couple. So this point is also important. So very, very important. If you know electrochemical series, you can find out the numericals based on electrode potentials easily. If you don't remember also, I have given you the tips how to identify which is cathode, which is anode. So I hope it is clear. Next. Now we'll see this electrochemical series table, very, very important. So stronger reducing agent down the group. Stronger reducing agent means here lithium is top. Lithium is the strongest reducing agent. Sodium is next strongest. Magnesium is next strongest. Aluminum. By this you can say lithium can displace sodium from its salt solution, but sodium cannot displace lithium from its salt solution because lithium is placed in the top. That is the stronger reducing agent down the group here they have given. So you can identify. So that is the value is minus 3.04 electron volts, and whereas minus 3.04 volts, and sodium minus 2.75, for magnesium minus 2.37. Like that, zinc we have zinc gaining 2 electrons from zinc ion, zinc. So it is minus 0.76 volts. So more the negative reduction potential, strongest is the reducing power. You can write the statement here. More the negative reduction potential, stronger is the reducing power. Here we don't have place. I'm taking new slide. More the negative. This negative means only the number, not the value. More the negative reduction potential, RP. Stronger is the reducing power. Stronger is the reducing power. So lithium can displace any metal from its solid solution because it is on the top of the table. That is at the base here they are given, but actually it is on the top. So because we have to see the table from lithium up to fluorine. Fluorine is the weakest one. So the one, so here lithium can reduce any metals like sodium, magnesium, aluminum, zinc, iron, cadmium, nickel, lead, cobalt, copper, tin, hydrogen, oxygen, anything, all the metals. So this is the way we have to see the electrochemical series. This electrochemical series is very, very important. And here, this is stronger oxidizing agent. They can bring oxidation. They can bring oxidation to the substances. For example, here, you can see here clearly, F2 changes to F minus. H2O changes plus 2H plus gives us 2H2O. MnO4 minus. So here, hydrogen after we have tin plus 4. Actually, tin should come plus 2 states should come before. And after hydrogen, we have copper, silver, gold only. After hydrogen, we have copper, silver, and gold. So copper can displace silver from its salt solution. and copper can displace gold from its solution because copper is far above than silver and gold. You can see as this is silver and this is gold. Ag is silver and gold also they have mentioned. They didn't mention here. So this is the strongest reducing agent down and the strongest oxidizing agent up. Weaker oxidizing agent up and the strongest reducing agent down. I hope it is clear. So this way we have to see electrochemical series. Next. So zinc displays hydrogen from its acids while copper does not. Why? Because the half cell potential of zinc electrode is negative with respect to standard hydrogen electrode, whereas for copper it is positive. So positive cannot displace the hydrogen and negative can displace hydrogen from its salt solution, as I already told you. So the metal which has negative reduction potential can displace hydrogen from hydrogen, whereas the metal with positive reduction potential cannot displace hydrogen. So since copper is having plus 0.34 volts and zinc is having minus 0.76 volts. So zinc is nothing but minus negative value reduction potential, that is Z E degree of Zn plus 2 to Zn is equal to minus 0.76 E degree of, here I'm writing, you can note down, E degree of Zn plus 2 change to Zn, salt change to Zn is equal to minus 0.76 volts, which you have got it from experimental calculation, whereas E degree of Cu plus 2 to Cu gives rise to plus 0.34 volts. So the electrode metal which is having positive electrode potential cannot displace hydrogen because hydrogen is electrode potential of hydrogen is how much? Zero, because it is. So it cannot displace hydrogen, whereas the metals with negative reduction potential can displace hydrogen. So I hope it is clear. Very, very important. Next. Zinc sulfate solution can be stored in silver containers while silver nitrate solution cannot be stored in zinc containers because zinc sulfate solution can be stored in silver containers while silver nitrate solution cannot be stored in zinc containers because zinc can reduce silver nitrate to silver, but silver cannot reduce zinc sulfate to zinc. That's simple. So silver is below in the electrochemical series and zinc is above. So zinc can displace silver, but silver cannot displace zinc from its salt solution. So zinc sulfate is a salt solution. It can be easily stored in silver because it cannot reduce zinc sulfate to zinc. Whereas while silver nitrate solution cannot be stored in zinc containers because zinc can reduce silver nitrate to silver. So that's why we cannot store. I hope it is clear. Next. So half cell potential of zinc electrode is less than that of silver electrode. Next we have so electrode potential topic. We are going to finish. Very, very important. So Nernst equation for single electrode. So for single electrode like copper, magnesium, manganese, zinc, etc. Anything. So for example, let us see Mn plus is a single electron metal with positive charge. N plus, it can be 1 plus, 2 plus, 3 plus, and so on. So Mn plus N electrons, gaining N electrons, it forms M. So whatever the charge, it should gain that much N electrons. So for example, if N plus is 2, so 2 electrons should gain. So let us take single electron potential. The Nernst equation is given by Mn plus changes to Mn plus changes to M is equal to E degree of, that is E degree of cell minus RT by NF, where R is called gas constant, T is called temperature, and N is called number of electrons, F is called Faraday. And you know Faraday value, temperature, and R value are constant. So log, natural logarithm, concentration of M by concentration of Mn plus. Since concentration of M cannot be there because it is a solid, usually metals are solid, so we will take it as unity, that is 1 by Mn plus. So this is called representation of, to calculate EMF of the cell by using Nernst equation. This is called Nernst equation. So it is also called as Nernst equation for single electrode. So for single electrode, we have to take, since Mn plus is reactant. So for reactant Mn plus, this is having concentration. So we'll keep 1 by, and product, this is M, and M should come here, product should come here, but here M, since the metal is solid, so for solid we don't have concentration, so the concentration of solid is taken as unity, that is 1. So always EDQ of cell, EMF of the cell is equal to EDQ of cell minus RT by NF into natural logarithm of concentration of products by concentration of reactants. Here concentration of product is M, and so as it is solid, it is taken as unity. So in this way we have to determine the single electrode potential or reduction potential. Next, so Daniel cell for copper and zinc, you can see here. So EDK of cell is equal to, already we know, EDK of cathode minus EDK of anode, and cathode is Cu plus 2 to Cu, anode is zinc plus 2 to Zn, right minus left. So how will you apply this? EDK of cell is equal to, that is EMF of the cell is equal to EDK of Cu plus 2 to Cu minus, so simply you can write straight away EDK of cell, because the second step is quite confusing. No need to take this. Simply you can write EDK of cell, that is EDK of Cu plus 2 to Cu minus EDK of Zn plus 2 to Zn minus RT by, so number of electrons involved in this case is 2. So 2F natural logarithm zinc ions. As I told you, zinc ion is the product and copper ion is the reactant. So copper ions is the reactants. So products we have to take concentration and reactants we have to take concentration. So EDK of EMF of the cell is equal to EDK of cell minus RT by 2F IN, that is Ln, that is natural logarithm Zn plus 2 to Cu plus 2. In this way, we represent in this equation. So here product and here reactant. Or you can say here oxidized form by reduced form. Oxidized form by reduced form. You can write here. Here I'm write oxidized form divided by reduced form. Always you should think like that. Oxidized form by reduced form divided by reduced form. Because oxidized means zinc changes to zinc ion, and reduced form means Cu plus 2 changes to Cu ion. So I hope it is clear. Next, I'm clearing the drawing. So in general, for a cell with cell reaction, A moles of A plus B moles of B gives us C moles of C and D moles of D. EMF of the cell is equal to EDK of this total cell minus 2.303 RT by NF log Q, where log Q is nothing but log of concentration of products by concentration of reactants. Since 2.303 RT by F is at 298 kelvins is 0.0591, straight away we can write nearest equation EDK of cell is EMF of the cell is equal to reduction potential of the cell minus 0.059 by N, where N is called number of electrons, log Q. Log Q is nothing but concentration of products raised to their stoichiometric powers by concentration of reactants raised to their stoichiometric powers, which is also can be taken as log K. Kc also. At equilibrium, we can take it as Kc. So I hope it is clear. Next. Now we'll see questions based on this. Calculate the cell potential of the following cell given SRP values of magnesium Cu is given. So from by seeing this, we can say magnesium is anode because it is having negative value, and copper is cathode. So magnesium is anode, copper is cathode. Even they have given a cell representation also. If they don't give cell representation also, we can write. And they have given the concentrations of magnesium ions as well as copper ions. So applying this equation, first we have to find EDK of cell. EDK of cell means electrode potential of the cell is equal to EDK of cell is equal to EDK of right minus EDK of left, right minus EDK of left. So by substituting that values, 0.34 minus of minus 0.236, 2.36, because minus becomes minus of minus plus 2.36. So 2.36 plus 34 is how much? Is equal to 2.7. 2.7 volts. 2.70. 2.70 volts. Now EMF of the cell E is equal to, applying Nernst equation, EDK of cell, that is 2.70 volts minus 0.059 by N. N is nothing but what? Here 2 electrons. So N will write N into log of concentration of, first we have to write Mg plus 2, Mg plus 2, because it is product, divided by no log. I'm writing it clear. So Mg plus 2 divided by concentration of Cu plus 2. So this if you substitute, you'll get the answer. So EDK of right minus EDK of left, that is 0.34 plus 2.36. So you'll get the answer. EDK of cell is 2.70 minus 0.059 by 2 because 2 electrons involved into log of 0.05 divided by 0.1. So if you cancel out, you calculate, you'll get the answer. I hope it is clear. Next. So answer could be 2.708 volts. You can verify the answer. That is the EMF of the cell. EDQ of cell is different. E of the cell is different. EDQ of cell means reduction on standard electrode potential. And E of the cell is EMF of the cell. That is E of cell. So I hope it is clear. Next example 2. Calculate the single electrode potential of copper electrode. Here copper electrode dipped in 0.05 molarity copper sulfate solution. So you can write E is equal to single electrode means I told you E is equal to EDK of cell, that is copper electrode, minus 0.059 by N into log of, writing it again here, place is not there, EDK, EMF of the cell is equal to EDK of cell, that is copper cell, minus 0.059 by N into log of concentration of, sorry, into log of 1 by, because here it is only single electrode potential. For single electrode potential, the product is metal. So product is metal means copper. So for copper there is no concentration because it is solid. So we take it as unity by Cu plus 2, concentration of Cu plus 2. Now this is equal to 0.34 because it is already given 0.34 minus 0.059 by 2 into log of 1 by, where the concentration of copper is given 0.05. So after this, you can do calculation. So the 0.05 can be taken as 5 into 10 to the power of minus 2. So you can use and you will get the formula. So EMF of the cell is equal to 0.301, whereas EDK of cell is equal to 0.34. This is only single electrode potential. For single electrode potential, you have to use this formula like this. Because in single electrode potential, already you get the metal. This is single electrode potential. Already given there. I hope it is clear now. Next. Single electrode potential. Next. Example 3. Calculate the potential of hydrogen electrode which is immersed in a solution of pH is equal to 10. They have given pH. This is also single electrode potential. They are asking potential of hydrogen electrode which is immersed in a solution of pH is equal to 10. So pH is nothing but negative logarithm of H plus. pH is equal to negative logarithm of H plus. And H plus concentration is taken as that is pH is equal to 10 means that is equal to 10 to the power of minus 9. Because 10 to the power of minus 9 is the H plus concentration. H plus concentration, negative logarithm of H plus. So H plus concentration is equal to 10 to the power of minus 9. So this concentration you have to take because this is also single electrode potential. So E is equal to E degree of hydrogen, H plus to H. E degree of H plus to H minus 0.059 by N into log of 1 by concentration of H plus. Since hydrogen is H2 molecule, we have to take 1 by concentration of H plus whole square. And here number of electrons is 2. So this will become like this. Now since E degree of H plus by H, they will not give because it is standard hydrogen electrode, it is taken as 0. So 0 minus 0.059 by 2 because 2H plus uses to H2. The log of, but anyway 2 not required, 1 only. Here also 1 only will take because half H2 also we can take. Half H2 also. So it is 1 and here no 2 is required. So by 1 because only 1 electron required for 1 H plus into log of 1 by 10 to the power of minus 9 because that concentration is getting from pH. So you'll get the answer by calculating this. And the answer is 0.591. You can calculate minus 0.591 is the answer. So it is clear. So in this section we discussed about electrode potential Nernst equation, and all other things. So this lecture is very, very important. So lecture 3 we have finished. In lecture 3, what we have covered: electrode potential, standard electrode potential, Nernst equation, and how to do problems based on it. And more about this session we'll do in the next hour. I hope it is clear. Thank you all.